briefly, I'll begin with some background, move into what my research looks at, and finish with a summary and some possibilities for future research. But to begin, the planets of the solar system are subject to gravitational perturbations from various sources, including those from other planets, from asteroids, and effects such as general relativity and solar latence. Now, despite recent observations of planetary positions, the uncertainty in Mars's position is actually reported to be up to 1 kilometer, and the largest cause of this uncertainty is the main asteroid belt. Specifically, the small and medium mass asteroids within the asteroid belt are the largest causes of uncertainties because for them we don't have accurate mass estimates, and so we can't accurately include them in our numerical models. Now, to give you an idea of just how complicated the mass distribution within the asteroid belt can be, there are over 560,000 objects known today, all varying in masses over several orders. Now, there have been several studies that have looked into characterizing asteroid perturbations in the past, but they've all looked at further refining high-precision ephemerides. Ephemerides are just tables of planetary positions. Now, first, Yang and Simon 2005 considered a 300-object model, and their results are of interest in my particular research because they find that asteroid perturbations on Mercury and Venus are actually non-negligible. Now, the question in my research is whether or not second-order perturbations from these planets are negligible, because if they are indeed, I'll be able to remove them from my integration and thus reduce integration times without sacrificing accuracy. Second, Chinka et al. 2010 analyzed modeling the main belt as a ring, and their results are of interest simply because in the future I actually plan to implement a smooth mass distribution to model the main belt. Now, finally, Lascard et al. 2011 look at the chaotic interaction between asteroids, and their results are of interest because they are the same nature, or a similar nature to those which I obtained in this study, namely an accuracy limitation. Now, in order to do this, I've first developed a new approach which actually does not seek to refine high-precision ephemerides, but instead looks at characterizing perturbations from the noise perspective. The analogy I like to use is that of a radio. You can consider it the ideal unperturbed planetary system of only 8 planets, as listening to the radio in the city. It's a clear and crisp signal. However, when you go under a high voltage line, you naturally get some noise in your radio signal. And the same thing actually happens with asteroid or with planetary motions. When you include asteroid perturbations in those motions, you get a noise in that ideal signal. Now, in order to model asteroid perturbations, I've actually developed an integration framework to model Newtonian solar system interactions. And before proceeding for calculating my results, I've actually determined that the numerical noise of the framework is several orders of magnitude below asteroid perturbations, or below the gravitational perturbation signal. And this ensures that whatever signal I do observe is legitimate and not simply an artifact of numerical noise. Second, I also compare my results to those found in the JPL horizon ephemeris to find that they're actually closely related, meaning that my integration framework is rather accurate. Now, in this study, I actually only consider perturbations from the 8 planets or the 300 largest asteroids, and the 300 largest asteroids together make up 95% of the mass of the asteroid belt. Now, I also only model Newtonian interactions, and for this project, because it does not further seek to refine ephemerides, leaving out perturbations or differences in relativistic effects is actually not problematic, because the accuracy needed is not of that order. However, a key point in this project is the notion of residuals. Residuals are simply differences between integrations with and without different subsets of asteroids. So I specifically compared integrations with 8 planets to integrations with the 8 planets and 300 asteroids, and take those differences for one orbital element for one planet, for example, the semi-major axis of Earth, and analyze those using power spectra. Throughout the presentation, you may hear me speak of the 300 largest asteroids modeled as point masses and about implementing a smooth mass distribution to model the main belt. And as an aside study of this project, I've actually done a brief look into the distribution of mass as well as orbital elements within the main belt. So presented here is a 2-dimensional histogram showing semi-major axis and eccentricity. And although it varies from 0 to 0.35, it can actually be considered fairly uniform. However, when we now look into the orbital inclination of the asteroid within the main belt, we can see that it ranges anywhere from 0 to 25 degrees, indicating that a ring oriented in only 2 dimensions is likely not accurate enough to model asteroid perturbations, and thus a ring will have to be oriented in a 3rd spatial dimension. Now, Furthermore, you can see there are several groupings by semi-major axis actually caused by resonant interactions with Jupiter. Those groupings indicate that most likely several concentric rings will have to be implemented in this model in order to attain fullest accuracy. However, returning to the residuals, I analyzed them using something called Fourier spectra or power spectra. This essentially places a signal in the time domain into the frequency domain, and they are very useful for noise characterization. So here I present a slide showing the perturbations or the power spectra of the perturbations from the 300 largest asteroids onto Mars. And the key thing to notice here is the presence of a clear 1 over F noise at the lower frequency. Now, this result is interesting simply because 1 over F noise permeates physics, and it's now also showing up in the Fourier spectra of perturbation residuals. However, the most interesting result of this research is actually that there is a noise floor, a white noise floor, at higher frequencies, and this noise floor actually precludes the knowledge of planetary position. That is, because the noise floor is consisting of white noise, which has random amplitudes, it is impossible to predict planetary motions on the order of centimeters and millimeters. Now, you'll also notice that in those plots there was a dense collection of spectral lines, and this dense collection is likely due to resonant interactions between asteroids and planets, planets and asteroids, and asteroids and asteroids. However, you can also notice in the lower frequencies that there is some spectral broadening. There are wings that are coming off of the spikes. And a possibility for this is actually that there are chaotic interactions present within the main asteroid belt. And in the future, I actually plan to implement something called the MEGNO indicator. MEGNO stands for mean exponential growth of nearby orbits. And it's a mechanical tool or a numerical tool to quickly and efficiently calculate whether or not an orbit or a system is stochastic or chaotic. Also in the future, I plan to implement the smooth mass distribution. And I'll actually be at the Naval Observatory this summer where I hope to complete this research. Now, in summary, the asteroids are once again the largest cause of uncertainty in planetary motions, and specifically the small and medium mass asteroid. Now, in order to model their perturbations on planets, I've developed a framework to model Newtonian solar system interactions, and I found that through looking at the Fourier spectra of the residuals, there is an intrinsic accuracy limit in planetary position. So, whereas other studies have asked the question, what is the most effective way to obtain accurate results for ephemerides? My research actually says that no matter what you do, you actually can't get more than centimeter and millimeter accuracy, simply because asteroid perturbations preclude that number. So that concludes my presentation, and thank you.